you can get started. It's 3:32. So let me just say that it's a great pleasure to have today with us Anne-Marie Madigan, coming from the University of Colorado, Boulder. Interestingly, Anne-Marie and I will soon have a common academic offspring. So when we realized that we would have an event tomorrow taking place with Jane, I was like, well, what a great opportunity. We should actually have Anne-Marie also give us a talk. So here she is today. So a few words about Anne-Marie. She got her master's and PhD from the Leiden Observatory in the Netherlands in 2012. Then she was a NASA Einstein Fellow and Einstein Fellow, right? And also a theoretical astrophysics fellow at the theoretical astrophysics at Berkeley and theoretical astrophysics center at Berkeley. And she was there until 2016, and then the University of Colorado Boulder snapped her. She got a faculty position there where she is until today, and she is an associate professor. She's an expert in things that have to do with gravity, gravitational dynamics, of stars and gas around black holes, N-body systems. When you have a collection of particles and all these things, she really knows, how to deal with all these things. And today, she will be telling us about forming the Kuiper Cliff. So,
Thank you so much. Is somebody monitoring Zoom?
Yes.
Yeah. Okay. Great. Just to make sure people can hear. Okay. Well, thank you so much. I am honored and terrified to be giving a talk on the Kuiper Belt in the Kuiper Space Sciences building. This is very much unpublished work. So this is the first time I'm actually presenting on this particular topic, the dynamical mechanism to truncate our solar system, create something called a Kuiper Cliff. So with that, I will get started. I do want to highlight the reason that I am here, which is that Jane Bright is defending tomorrow. So her defense is at 1 p.m. and the first part is public. So she'll be talking about aspects of supermassive black hole mergers, the stars and the gas that are around for that event. And I also want to say that Tetsuya Akiba, finishing grad student in my group, I believe gave a talk today.
I did, yes.
You did, and he will just never stop talking. So there's another talk on Friday on a different topic. Today was quite dwarf accretion. Tetsuya will be talking about time disruption events on Friday, I believe. Yes. Okay, so these are students who are working on supermassive black hole dynamics. I'm also quite interested in our outer solar system. And in particular, as I said, this problem of how to actually truncate our solar system. And I'll explain why we think it actually has an edge. So in preparing for this talk, I was interested to see, do we have a local analog of our solar system, but when it's still in its active planet formation stage, when this truncation process would have happened. And we do. And so apologies to those in the room who actually work on protoplanetary disks, maybe should have been aware of this system. Apparently this is really famous. So this is TW Hydra, or Hydrae. This is a beautiful ALMA image. The star in the center is about 80% the mass of our sun. So similar in ways, except it's really young. So between 5 and 10 million years. We can see we have this protoplanetary disk of gas and dust that has a radial extent of about 200 AU. So keeping that in mind. We also see there are internal dynamics going on in this disk, carving out gaps, rings. So there's actually a likely planet candidate at about 20 AU that is Neptune mass. And this I find really interesting for the purposes of this talk, actually. Neptune mass planet at 20 AU. It's kind of suggestively nod back to me. Yeah, cool. Point of showing this, though, that this is really close. It's the analog of our solar system during the early phases of planet formation. Okay? So very large radial extent, not truncated. Now to go to a schematic of our solar system before showing you some data of the outer edge. This is to kind of set up the regions of space that I'll be interested in the talk. I've got semi-major axis, so looking at orbit space here, semi-major axis in AU on the log, in log on the x-axis, and going from 0 to 1 in eccentricity on the y-axis. So I'm interested in the outskirts of our solar system. So we've got Jupiter, Saturn, Uranus, and Neptune on their circular orbits. We've then got the Kuiper Belt. So this is this vast reservoir of planetesimals left over from the epoch of planet formation that extends from 20 to 30 to 50 AU, and is similar to the asteroid belt, but is far wider and far more massive. So 20 times as wide, 200 times as massive. Okay, but it does seem to have this edge, which is called the Kuiper Cliff. I'll get into that soon. We also have a scattered disk, or these are bodies that are very similar, so icy planetesimals left over from the epoch of planet formation, but they live in a dynamical region of space in which these bodies are moving on orbits where they gravitationally come in very close proximity to Neptune at perihelion. And when they do so, they go to perihelion, they get close to Neptune, they can be accelerated or decelerated along their orbits. That gives them a boost in energy, decreases the orbital energy. If they get a boost in energy, they're still on a Keplerian orbit-ish about the sun. So they get a boost in energy, they'll move to a larger semi-major axis orbit. They will come back though to where they felt that initial boost. And so in this way, they actually move along this line of constant perihelion with Neptune. And perihelion is given here by Q, the semi-major axis times 1 minus eccentricity. This is actually this line of constant perihelion, like moving back and forth. This is the dynamical pathway by which we think planetesimals moved out to the Oort cloud early in the epoch, the evolution of planet formation in the solar system. These bodies interacted, the giant planets moved outwards along these pathways. Okay, one more class of objects that are interesting for this talk. These are called attached objects. Again, very similar Kuiper Belt objects and scattered disk objects, small bodies, icy bodies. But these detached objects differ in particular from the scattered disk objects in that they can have a large range of semi-major axes, but they're not touching at perihelion any of the giant planets. They're detached in the sense that their eccentricities are smaller, which means their perihelion distances are much larger than any of the giant planets. So if they got to their current locations of hundreds of AU, it's not clear how they actually managed to detach themselves from the bodies they were scattering off of. Okay. Excellent. Great. No questions, I'm going to assume. So here's to show you some actual data. This is from a recent paper by Volk and Malhotra. And what you're seeing here is, again, semi-major axis versus eccentricity, but it's color-coded. The bodies in black are going to be, well, maybe I should say the bodies that are not in resonance with Neptune are plotted in green. You can see, though, that there are many bodies in resonance with Neptune. Neptune here is at 30 AU. Here we have the Plutinos. So Pluto is a part of this population, 3 to 2 orbital resonance with Neptune. And this is really nice evidence of Neptune's outward migration. We believe Neptune formed, I'm going to go back to the around 20 AU. Believe Neptune formed much closer to the sun, migrated outwards because of this interaction with planetesimals. You made a planetesimal, if you happen to scatter it inwards, you'll get a corresponding boost in your angular momentum and get pushed outwards. So you can capture these bodies in mean motion resonances really nicely, also explain why their eccentricities get pumped up, this mean motion resonance capture mechanism. And the other thing I want to point out here is this drop off in the number of bodies after about 48 AU. This is where Neptune's 2-to-1 mean motion resonance is. Not quite clear if the cliff is at 48 AU, just at the 2-to-1 mean motion resonance, 50 AU, but it is clear, the scale from 50 to 150, that there is an absence of low eccentricity, low inclination Kuiper Belt objects beyond this point. So this is what is referred to as the Kuiper Cliff. There are many papers on this topic. This is the first. Okay, so what I want to get into here is this idea of just disk truncation. There are other bodies here, the green ones, that are not in resonances, and it's not clear to us yet whether or not these bodies that are painted green here that are not in resonances, if they formed in situ or they formed closer to the sun and got pushed outwards. Maybe we're in resonance and dropped out. This is one scenario. But either way, we need something to truncate the outskirts of the solar system. If they formed in situ, there are many papers, this is an example of one, that show that to actually form large bodies at this distance, you would need a lot of mass to exist in this region of the solar system during the epoch of planet formation. You can't have a low mass disk and then expect to form massive bodies similar in size to Pluto. Okay, so if those bodies formed in situ, we needed a lot of mass there. Right now, the mass constraints are less than 0.1 Earth masses. So where did that mass go, is the question. If they did not form in situ, but formed closer to the sun and got pushed outwards, why was there no mass there? Where is the mass? Like, where did the mass go? Comparing it to the TW Hydra disk. That's visibly extended to 200 AU. So why is our solar system different? Okay, so we got mysteries. I'm going to go through each just in separate slides to make sure we're all on board. But the first one is that there's a current modern day Kuiper Cliff at about 48 to 50 AU that is, we're pretty sure now is a significant drop off in the surface density or number density of Kuiper Belt objects. Okay, there are various other ways to actually explain the observed drop off, like maybe as you go outwards in semi-major axis, you have a cutoff in the size of Kuiper Belt object. You can actually form something like this, but it has to be really, really steep to explain the fact that you don't see that many bodies beyond 50 AU. I will get to why Neptune, we understand that it migrated. We don't yet understand why it stopped at 30 AU. There are lots of different ideas. But I'm going to wrap those two up together and just say it would be really nice to get a way to truncate our solar system in a natural way that either explains the Kuiper Cliff or Neptune migration at 30 AU or both. So I'm going to propose a mechanism to truncate disks in general. I'm not going to try and hit those numbers in the talk. It's a very early stage project. I'll just present the mechanism to you, how it works, and then go back and do all the actual simulations to try and hit the numbers quantitatively. I also explained the detached objects, and I'll talk about orbit clustering in the outer solar system. The mechanism I'm going to propose can explain these three things: disk truncation, detached objects, and orbit clustering. Okay. For the Kuiper Cliff, as I said, this is just this unexpected drop-off in number of observed Kuiper Belt objects beyond 48 AU. There are many observational papers trying to figure out if this is a real effect or if there's something else that can explain why it just seems to sharply drop off. There have been many proposed explanations. So just mention a few, and again, not give an exhaustive list of papers. One is Planet X. So just the idea of introducing a massive planet outside of 50 AU. This would act like Jupiter does on the asteroid belt, kind of familiar with these types of dynamics. We have not detected a Planet X, but it's still a possibility that one exists. A close stellar encounter is another idea that our solar system, of course, did not form in isolation. It should have formed as a part of a star cluster. So stars would have been passing closer to each other than now, 4.6 billion years later, when we have actually been loosened from that original stellar cluster. And so a close stellar encounter of a star actually passed by with a perihelion distance like 100 AU or something like that on just the right orbit could excite the eccentricities of these outer Kuiper Belt objects. The latest paper that I've read on this in 2018 was unable to find a good fit to actually explain the outer solar system, but it is still a possibility. Collisional erosion was an idea put forward in the late 90s. I'm sorry, I have a Mac, but occasionally I have to install Microsoft things. Which just never happened. The idea that, again, if you can excite the eccentricities of these Kuiper Belt objects outside of 50 AU for whatever reason, they can go on to crossing orbits, collide with each other, and actually erode to the point where radiation forces will change the orbits of the remnant particles. This doesn't seem to work right now, as far as I'm like my frantic literature search, mainly last night at 10:30, just because of our increased understanding with the New Horizons missions of, our class and other Kuiper Belt objects not looking like they've been collisionally eroded, that they're a little more pristine, so not quite fitting in with this theory. There's also gas-dust dynamics, or the interaction with dust and the gas. One example is by Andrew Newton and Shu here, looking at dust radially drifting inwards and actually being evacuated in the outskirts of the solar system. So being unable to actually form planets. Okay, so there are other theories, particularly the first two is kind of like more of an external idea. There is something out there that can truncate the solar system. So with this hypothesis, we're thinking more something that will work inside out and should work for pretty much all planetary systems. Okay, so that's the Kuiper Cliff. We've got like 4 things together. So halting Neptune's migration. So I just want to explain this really briefly with this schematic. This is coming from the original paper by Fernandez and Eep, where they were looking at not just a single planet interacting with the disk of planetesimals, but looking in particular at our solar system, the fact that we had at least 4 giant planets in a row, and they were actually interacting with each other and planetesimals at the same size, not not in isolation. Okay, so what I'm drawing here schematically is Neptune and this outer disk of planetesimals, which is a pretty common setup in these simulations to think that at some point your planet forming efficiency would drop and you would be left over with smaller bodies outside your last official planet. So you have this remnant disk extended beyond Neptune. If one of those planetesimals has one of these strong encounters with Neptune, if it just gets scattered onto higher energy orbit, there's no real exchange of energy and angular momentum here. But if it gets scattered inwards, Neptune would move outwards as a result, just a very tiny amount, okay? But you could also say, well, the same thing would happen with some planetesimals over here, same, are you really moving inwards or outwards? It's going to be really about like surface density profiles in particular. But because Neptune was not in isolation in this disk, there was another planet, Uranus. You can have a motion of planetesimals from outside Neptune's orbit inwards until it meets a much bigger planet called Jupiter. And Jupiter has such a large escape velocity relative to the escape velocity of the sun at that distance that it can actually eject planetesimals quite efficiently. And so in this way, our solar system with the 4 planets, and in particular an inner planet that's much more massive, this means there's a net sink inwards of Neptune, that it can pass planetesimals inwards that can get ejected by Jupiter. But you don't have that same sink on the other side, at least in the standard Fernandez-Eep scenario. And so this led to a very straightforward picture, like accepted picture that Neptune migrated outwards, and then with the mean motion resonant capture theory, is really well accepted. Your problem is how to get Neptune to stop migrating. You have an extended non-truncated disk. So it's an example from Gomez et al. In 2014 or 2004. You have an extended disk going from 20 to 50 AU, for example. These are the semi-major axis evolution lines for Jupiter, Saturn, Uranus, and Neptune. See those three outermost planets all migrate outwards while Jupiter actually migrates inwards. Neptune just keeps going to the edge of the disk. It can even go beyond the disk because it's all a matter of how much angular momentum is actually stored in these planetesimals, not so much their mass. So lower mass disk, but still extended to 45 AU, it still migrates to the end. These reversals are really cool. It's all about the relative number of planetesimals on either side and how much angular momentum is stored one side or the other. You can go to a lower mass disk. So for example, this is Han and Malhotra in 1999. This is a 10 Earth mass disk, this is 50 Earth mass disk. You can construct disks with certain profiles that will actually make Neptune stop just right around 30 AU. The problem here, of course, it doesn't migrate enough. Problem here, it migrates to a really nice point, 30 AU, but there's still material further out. You just dropped below a critical density. So you can stall, but then you're left with the rest of the disk material. You don't see that. So where did it go? How do you get rid of it? Okay, should I mention this now? Yeah, okay, so if you're left, for example, in this situation here with the 50 Earth mass disk, if you're left with, say, 10 Earth masses of material, 20 Earth masses of material beyond the orbit of Neptune, and now you say, this is fine, I'm just going to excite the orbit somehow to get them onto high eccentricities. You're going to interact with Neptune, and Neptune's just going to scatter them away. The problem with just doing that is that Neptune will still be interacting with planetesimals that have larger angular momentum than it does. And so it will continue to migrate out. So you can stop Neptune, but then you've got a disk that can't interact with Neptune. Well, something else is happening too, or else it will make Neptune migrate again. Stop Neptune, left over with stuff, get rid of the stuff. Okay, good. Like some nods of like, I get it. You're over-explaining. Okay, great. Okay, we've got four things. Third thing, I've already mentioned attached objects, but I just want to mention it again and also show this schematic from Mike Brown, which is really nice. So this is the inner solar system, looking top down at the orbits, moving outwards. We have the Kuiper Belt, we have the orbit of Pluto, really nicely eccentric. Now we have Sedna, which is the most famous detached object. This is its position where it was detected. But this is the orbit of Sedna. I find this really nice to show, particularly in undergrad classes, just how different this body is and how exciting it is. The detachment we're referring to here is that at no point does Sedna actually come near the giant planets. And there is no model of the original protoplanetary disk around the sun that would be accepted that would say we should have formed a body like Sedna, a planetesimal, at a semi-major axis of hundreds of AU. I forget now its exact semi-major axis, but it's close to 1,000 AU. So Sedna definitely did not form where we see it. How did it get there? Onto its current orbit. And then lastly, orbit clustering. So I've taken this obviously from a press release by Madigan and Brown in 2016, where they're looking at outer solar system objects. They've got Sedna here, which I just shown. 2012 VP 113 is still colloquially known as Biden, but just because he was VP in 2012, but I think eventually it will be given a real name, real designation. But the reason I'm showing this is when I'm talking about orbit clustering, what I mean is this apsidal clustering, or for those who do a lot of Keplerian dynamics, eccentric orbits have an eccentricity vector that points to their perihelion from the focus. So these are all the eccentricity vectors kind of pointing together. In 2016, Madigan and Brown were proposing that there's a planet 9 in our outer solar system. Planet 9 is shepherding, kind of like forcing, torquing orbits nearby lower mass objects onto one side of the sky, and that was the reason for orbit clustering. I'm going to show you one more plot here. This is from the same paper, but now we're looking at something called longitude of perihelion. This is just a measure of how clustered orbits are. If these points are all over the place, that means the orbits are all pointing in different parts of the sky. If they're clustered together, as they appear to be beyond, 200 AU, that means we're all pointing in the same part of the sky. I do want to say there is a real debate going on whether or not this signature of orbital clustering is real or it's all observational bias. So there are, two basic camps: real observational bias. Papers coming out, just even like looking at the same data and disagreeing with each other. So I'm not going to jump on board either camp. It's an exciting, weird signal that I hope is real, just because it's weird and it's more fun to have strange dynamical signatures you need to explain, then everything just works out beautifully for our solar system. But I do want to mention there are many people who would say this isn't real, it's observational bias. It's low number statistics, and every survey we do where we're able to characterize the observational bias, we don't actually see this type of clustering. Okay, so I've taken those 4 things. There is an observed Kuiper Cliff today. You need to halt Neptune's migration at 30 AU, which suggests that the disk was truncated at around 30 AU. How that relates to the Kuiper Cliff is still unclear. We've got the detached objects that are real, that can't be observational bias. And then we've got orbit clustering, apparent orbit clustering, that I bring up because this hypothesis actually produces it. For these first 2 things that actually have numerical values associated with them, I'm just going to squash this down to just being like, I want to show you a mechanism that truncates the outer parts of solar systems. Not worry about exact numbers at this stage. Okay, this new hypothesis is extremely simple to explain. So first of all, I'm just going to show you schematically what's going on, and then I'll show you the results of the numerical simulation. So we're back in the schematic with semi-major axis on the x-axis, eccentricity on the y-axis. We've got the 4 outer giant planets, and I'm just not truncating the disk. I'm saying there are planetesimals between the giant planets as expected, and the disk just extends, drops off in surface density profile. Don't know what that is, but there are some observations we could use to constrain it. And then we're going to say that the giant planets, no truncation of the original disk. We're going to say the giant planets migrated after the gas goes, and they're allowed to move around, interact with the planetesimals. The outer 3 planets will move outwards. I spent a really long time on that animation. And the outer 3 planets move outwards, Jupiter moves inwards slightly. And those planetesimals they interact with that are driving the migration, they can move inwards, they can move outwards. If they move outwards, they are now in the same physical space as the outer circular, non-truncated protoplanetary disk. But they're on eccentric orbits. And I'm just color coding them differently because they're on different orbits. They're the same planetesimals. Okay, just like located originally closer to the giant planets than the ones further out. And that's entirely it. That is the new hypothesis. I'm just saying those scattering planetesimals that are on eccentric orbits gravitationally interact with that outer circular disk. And to give you an idea of the mass, this, as I said before, is the dynamical pathway to forming a red cloud. So, we don't have very tight constraints on the mass of the Oort cloud, but we know we have at least an Earth mass of material, and in the Oort cloud, this is the way the material gets there along this pathway. So it's lots of material here, gravitationally interacting with the material that's here, and what happens. So what's key to this is that the interactions that are important here are not standard 2-body gravitational scattering. Okay, but it's torquing. I'll explain. So typically when we think about bodies interacting with one another, we say they're going to move past each other, but they exert a gravitational force on each other, acceleration that will change their orbits. And when they get close to each other, they can really change quite a close encounter extreme event. But it's also important all the small weak encounters that they have with other particles in the area. This is very kind of standard. It's called two-body relaxation. You get an Binny and Tremaine. And this is the idea of how stars and clusters and galaxies actually change their orbits with time and relax to some equilibrium configuration. This is not going to be as important. If we take those same bodies and say, okay, you're not on some random orbit and having incoherent random walks in your angular momentum and energy, angular momentum in particular, because you're actually repeating the same orbit again and again as you move around the sun in the outskirts of the solar system. So if you meet a body at one position, you're going to actually be having a very similar encounter as you continue orbit after orbit. A better way to say this is to orbit average this system. So picture spreading the mass of the body out along its orbit. And in this orbit average sense, you've got two massive wires that are actually gravitationally torquing each other or interacting with each other and changing each other's angular momentum. Okay. And this picture holds really well as long as the orbits aren't precessing really rapidly.
Do they have the same orbit period, these two objects?
Yes, so there's papers that show that bodies within twice the semi-major axis of each other torque each other the most. And it drops off quite quickly with semi-major axis. So yes, if this isn't even a real eccentric orbit here. This is very lopsided and roughly drawn. But yeah, so it's bodies that have similar semi-major axes to each other, torque each other the most efficiently. Okay, so you picture like a more circular orbit, a more eccentric orbit. You try and figure out like, what are they going to do to each other? In this orbit average sense, nothing about your gravitational potential is changing, so your energy is conserved. You're not going to change the semi-major axis of the orbit. What you will change, though, is the eccentricity. So I'm showing here is angular momentum is r cross v. You can calculate that anywhere along an orbit. The torque that you will experience as an orbit is just going to be time derivative and angular momentum with r cross f. You need to integrate that around your orbit. F is just the gravitational force. But with these two equations, and knowing that you actually have more mass in this orbit average sense at apocenter than pericenter, you can really quickly figure out what the torques are going to do to each other. A circular orbit's going to get more eccentric, and a more eccentric orbit's going to get more circular. So just like statistically, kind of obvious that that's going to happen. But again, circular orbit gets more eccentric because of this gravitational and torque, and the eccentric orbit gets more circular. And this is really key. So I'm going to show you results of really simple simulations right now. It's just a snapshot. We're running them with the rebound code, IAS15 integrator. It's a really high order integrator, and we need that because we have bodies on really eccentric orbits. We need adaptive time steps to actually resolve the high eccentricity orbits. And again, very simplistic, idealized setup. I'm pretending Neptune is at about 19 AU, and I've got an extended outer protoplanetary disk. So just planetesimals on circular orbits. I then, once the simulation starts, start scattering bodies inwards on scattering disk orbits. And they are moving along lines of constant perihelion. Just assuming Neptune is interacting with planetesimals, scatters them inwards, scatters them outwards. I'm only looking at the outer solar system. But I let these bodies gravitationally interact with each other. There's a surface density profile. There's initial masses. I can change any of these, but this is just to give you an idea of the actual mechanism. So I'll set this running, semi-major axis versus eccentricity. The scattering bodies get populated really, really quickly. Let's see. So the circular orbits, they become more eccentric. The eccentric orbits become more circular because of the gravitational torques. I should also say this region of space here, this is the line of constant perihelion with my imaginary Neptune. If any bodies hit this line of constant perihelion with Neptune, that means like their perihelion has touched the orbit of this Neptune. They should have a strong encounter. If they're originally a Kuiper Belt object, and so like you're removed, and I will half the time scatter you back, but scatter you back onto a scattering disk orbit. Okay, so again, if you get into this region, like if your orbit gets so eccentric that you're now touching Neptune's orbit, I'll say you're going to have a strong encounter eventually with Neptune. So you actually just remove that particle, and half the time you actually join the scattering disk population. The other half you'd actually get scattered inwards. You could be removed by Jupiter. Okay, so with no attempt to reproduce any quantitative numbers, just to point out that you have really cleared out your outer Kuiper Belt. And too few particles here in this code. But with more particles, this would be actually much smoother. I'll say that in a moment. You've also created a lot of detached objects. In the real solar system, of course, Neptune would be migrating somewhere around 38U. So now these would no longer be detached objects here. These would just be interacting with all the other giant planets. These would be your detached objects here. Just to show you, so if I don't remove the particles, if they touch the orbit of Neptune, so this is from a different simulation. I should say that the movie was 10 megayears. Here, I didn't have time to actually convert to years. I've still got in orbital periods. This is showing the orbits of 5 Kuiper Belt objects. So starting off with 0 eccentricities and then being launched to really high eccentricities really rapidly and really smoothly. So you see this isn't scattering, this is torques. Also wanted to show that you can produce really nicely retrograde planetesimals, but again, this is in a simulation where I haven't actually removed them once they touch the orbit of Neptune. They would be removed before they go retrograde, I believe. But you can see this looks really like Kozai-Lidov dynamics. Okay, so last night at 10:30, this actually happened. I was going through my remaining like 20 papers, just being like, this is not my usual field of research. I have to read everything fast as possible. And I came across this paper, stopped my heart. I go, you're kidding me. Neptune scattered planetesimals could have sculpted the primordial edge Kuiper Belt. I'm like, well, great. You know, like when you read in the papers, sometimes people will be like, upon revision, we discovered a preprint of somebody else's work that has found something similar to ours. And you're just like, ooh, I know what that feels like. I had 27 years to find this paper, but it was the night before I give the first talk on the topic. Okay, but I do want to, so this idea isn't new, but in this paper, what they have done here is propose that if you had a small number of very massive planetesimals, so above an Earth mass, located at the inner edge of the disk, and then these bodies were scattered by Neptune into the scattered disk population, they could scatter with your outer Kuiper Belt circular orbits and kind of fluff it up. So it wouldn't be truncating it, but it could excite the eccentricities and inclinations to better match what we actually see today in the Kuiper Belt. So it's scattering. It's not the same mechanism. They didn't actually run n-body simulations. So it's kind of like, I'm delighted I hadn't just, claimed to have discovered something new, and then it's 27 years old. But I do want to point out, so their idea really depends on there being massive bodies in the Kuiper Belt, more than Earth masses, to kind of excite the bodies through that two-body scattering that I mentioned. This mechanism that you can see clearly in the simulations are orbit average torques that are driving angular momentum changes. And if you just look at the secular timescale, so the timescale to change your angular momentum due to torques, divided by the two-body timescale, change your angular momentum due to just like random incoherent interactions that you get like in a plasma, for example, it's proportional to the individual mass of bodies, meaning that if your individual masses get lower, torques become more efficient. So it's relative to two-body scattering. So in these simulations where the bodies are way too massive relative to what they would be in a real solar system, these simulations actually have too strong scattering. So it's actually going to be a nicer result once we bump up the number of particles that we have and in reality. Okay, but yes, I said this. So as your individual masses decreases, the torques between orbits become more efficient by changing your angular momentum. Okay, I will go quickly through this and end and take questions. But just to explain why this mechanism can actually reproduce like in bulk, not quantitatively, these features. So the first is disk truncation. So what I've just plotted here from that really simple movie is the mass of the outer Kuiper Belt. I started with 100 Earth masses, not solar masses, 100 Earth masses, ran it for only 10 million years. And again, you get eroded or you get removed from the region if your eccentricity is pumped up to such an extent that your perihelion touches the orbit of Neptune, that I don't have migrating in the system. So this is what as Neptune migrates outwards, it gets easier and easier to be removed. So here you drop down by a factor of 2 in your mass of the Kuiper Belt within 10 billion years. I haven't run it further, it's a very simple simulation. Just to show that it is the scattered population that are driving these changes. It's not just like scattering interactions between the Kuiper Belt objects themselves. I ran another simulation with a massless scattering population. And you lose some mass, but that's just the inner edge of the Kuiper Belt bumping up against Neptune. Not really actually changing its eccentricity much, just kind of the disk is spreading. And some of them actually interacting directly with Neptune at low eccentricity orbits. Okay, so you can truncate the disk.
Can
Yeah.
you explain what you mean by massless versus massive?
Yeah, so in the n-body simulation, you can actually switch off the mass of a particle, which means it is a test particle. It's feeling the gravity of everything. It does not influence anything. Okay, I'm combining 2 and 3 together because I think they are directly related. So we want some way to halt Neptune's migration. And I already told you, it's not enough to halt Neptune's migration at 30 AU and just leave an extended disk and then later say, oh, that extended disk can interact with Neptune. It's like, no, Neptune's migration will kick off again. But what I believe has been missed before is that when you have this scattered disk population interacting with an extended circular disk, those bodies detach. So they no longer actually can bounce back and interact with Neptune. They're detached orbits. They're like sediments. And so just like we had a mass sink due to Jupiter taking planetesimals that are scattered inwards by Neptune and then ejecting them from the solar system, we actually have a mass sink if you detach objects. You scatter bodies outwards, they interact with an outer circular disk, they detach. And so Neptune has net inward migration because of that. And so you can actually stall or counteract Neptune's rapid outward migration with this mechanism. So you can create detached objects pretty easily from this mechanism. And you can also make it so Neptune doesn't just completely keep migrating further past 30 AU. Orbit clustering. Let me just show this again. This is a longitude of perihelion, which just shows like which direction our orbit's pointing. And I've split the population between primordial disk, that's the outer Kuiper Belt objects that are in circular orbits, and scattering planetesimals, ones that are being scattered outwards by Neptune onto eccentric orbits. So the blue ones are those original objects. And I have to say, this was a surprise. This was not something I expected. But this is one of those things, you know, when you like, for those who run simulations in the room, you just have standard plotting scripts at some point. And one of the things you'll also do is just like, I have movie scripts. You just make movies, you know, you're just like, what about this? And so to see this, like my group members will kind of know, I was just like, you're kidding me. Like, I'm getting orbit clustering in this project? Like, this is not expected. You can see it here. So these outer Kuiper Belt objects are pointing in the same area of the sky over a wide range of semi-major axes. I've known about this for a while, that this did it. I still haven't actually run the test to figure out exactly why, but I think I know, because I've seen it before. So very quickly, why would orbits actually do this? So I told you orbits exert gravitational torques on each other. You've got 2 orbits. In an orbit average sense, it's like massive elliptical wires that will torque each other, change each other's angular momentum, given by these equations. Semi-major axis is conserved in this orbit average approach, so you're just directly changing the eccentricities of the orbits. Normally, and I use that language on purpose because of Lynden-Bell, I'll get to it in a moment. Normally, if you're on a more circular orbit, you precess faster than an eccentric orbit, and precession is just the opening out of your orbit, right? One of the undergrads I worked with, and I told him this, he was like, oh, it's just like a kayak. So I always use this in my explanation. Like if you're in a short kayak, you can change your orientation, like precess faster than in a kilometer long kayak. It'd be really hard to actually exert the force to actually change your orientation. So in the same way, if you're a nice little circle, you can actually precess faster or change your eccentricity vector faster than if you're a really elongated eccentric orbit. And that normally means in a typical gravitational potential well, this is the way it goes. Okay, so what I'm proposing is for the outer solar system that this is Lynden-Bell's bar formation mechanism at work, but in a Keplerian potential as opposed to galactic potential. So Lynden-Bell pointed out, you have the bars in a lot of disk galaxies, and it's still not a completely solved field, but one way to actually reduce bars is to change the gravitational potential of your galaxy to make it go from this normal to, this language he uses, to an abnormal region. So let me show what happens. In a Keplerian potential, let's say you've got some overdensity of orbits. Some orbits cluster together just to random noise, just to chance. These are bodies that are on counterclockwise moving orbits. This is the velocity vector at aporeps. Precession is retrograde, so the orbits would be opening out this way. Let's say there is an orbit nearby. It's going to feel a gravitational torque from the pileup of orbits in front of it. If we look at those equations, so this orbit here has an angular momentum vector that's r cross v, so it's pointing out of the board. Whereas the torque, just again think like maximum mass in this orbit average system is located at apocenter. Maximum mass is located here. So the force, gravity force vector that it feels, this particular orbit is going to be directed roughly in its the same direction as its velocity vector. So this means the torque is going to be positive. So it's going to increase the angular momentum of the orbit or make it more circular. If you make it more circular, normally it means you precess faster. So you would just precess away from the overdensity. And so you wouldn't expect orbit clustering. So what Lynden-Bell showed in this paper is that normally you get an overdensity of orbits in a galaxy. There's gravitational torques between the orbits. They precess away from each other. But if you change the density profile of your galaxy, which is constantly evolving, you can get an abnormal region where just the opposite happens. You get more circular, you slow down in your precession, and then this catches up with you and you're caught up in this overdensity, and then orbits just keep clustering, clustering, and clustering until you change potential such that you're a really stable attractor. And so we've shown this before. This can work in solar systems if you change the gravitational potential. So all I have to do now is just go show it does. It changes that interaction of scattering bodies with your outer circular disk. Okay, so this is my kind of summary slide. Forming the Kuiper Cliff or forming some type of truncation can happen from inside out. If you have giant bodies that can scatter smaller planetesimals onto eccentric orbits, those eccentric orbits on their way outwards to the Oort cloud, where they can interact with like passing stars, galactic tides, their orbits changed. They have mass, individually low mass, but collectively very massive. They interact with an outer circular disk, excite those outer circular orbits in such a way that the mass gets removed. Okay, there are many remaining questions. I just kind of wanted to throw a few up here before actually taking some questions. I'm not sure if we have to go through all of them. Maybe the fifth one I think is kind of interesting. I'm interested in like changing parameters of these simulations, surface density profiles, or more particles, things like this, to see, do we always just produce a truncation of the Kuiper Belt and then just no bodies after some semi-major axis? Or, and I think this will happen, do you get a reemergence of the Kuiper Belt at some semi-major axis? We can kind of go through why I think that will happen. There's a recent paper in 2024 came out in August, noting the possibility that we've actually already detected the re-emergence of the Kuiper Belt at a heliocentric distance by 70 AU. But it would be interesting to hear people's thoughts on this. So that would be really cool if we could actually see, can you reproduce it or definitely not? Like this mechanism will actually just spread all your circular orbits completely. So I'll go back to the summary slide and take questions. Thank you.
Perfect timing. So we have questions. Todd?
So my question that was formed during your talk, you actually listed it, your last slide is number 2. Which is that there is
Yeah.
a very well-defined cold classical disk. And it is compositionally different than the rest of the Kuiper Belt. It's low inclination, low eccentricity, and the hypothesis is that this is a primordial population that is left over from the solar system and hasn't been disturbed. Your simulation shows you heating the entire disk, and so I would think that would completely wipe out the cold classical disk.
Yes, so that's been something I've been thinking about a lot. So round of simulations that I need to do are actually putting in real planets. Because, and I think I've mentioned, yeah, the torque strength. Torques between orbits depend on your orbits not precessing rapidly, right? In order to change your eccentricity. So if you have the giant planets, there is a very steep dependence of apsidal precession. So anything very close to the giant planet region will be precessing really, really quickly. And so it'll be very difficult to torque those bodies. I don't have them in these simulations. That's like, answer number 1, no idea what's going on with them. My understanding of the literature is like, there's a lot of, it is unsettled what's happening there. But if I were to try to reproduce something like that, I think it'd be really important to put in actual giant planets that induce rapid precession and see, do you actually retain any low eccentricity orbits because they just can't be effectively torqued? I don't know. The fact that they're different color binaries, like it's
Yeah, it's a real thing, so.
yeah, no, absolutely.
In the back?
Have you included anything like the oscillus kernel in the disk?
The OSIS kernel?
It's the outer solar system, I forget what the last O means, survey.
Yeah.
Those are the CFHT. So one of their models has like the cold classicals and then the hot and scattered, but there's kind of like this area that like the cold classicals are like really bunched together, kind of.
Yeah, like I know there exists a Kuiper Belt kernel.
Yeah.
At some point, yes. Not at all. I have not included it. I've definitely not reproduced it in these simulations at all. But I think this is very much related to the fact that like there are Kuiper Belt objects that look like they formed in situ, like they have different colors, they're dynamically cold. They look quite different than the other Kuiper Belt objects. So trying to actually reproduce both populations seems really challenging. But I'll try.
Yeah, I didn't really understand the initial conditions for your experiments that you reported. You have already created a Kuiper Belt, which was created by scattering planetesimals off of the major planets in the inner solar system out to that region.
So I have initially a cold outer Kuiper Belt. So a cold disk of planetesimals
How did that form?
outwards of the giant planets. And just assuming that we had a large disk of planetesimals, many of them smashed together and formed planets, but beyond a certain point, they stayed small. So I had that as my initial condition. And then I scattered bodies outwards onto high eccentricity orbits. mimicking this, planetesimal driven migration, driving a lot of planetesimals outwards onto high eccentricity orbits as they go into the Oort cloud.
Okay.
The TW hydrates.
I'll talk to you tomorrow.
Thanks for a great talk, Anne-Marie. So in your A versus E plot of the rebound experiment you did, it seemed like there was actually another population of circular orbits around about like 180-ish AU, if I'm remembering correctly, and that kind of looks like your canyon there in point number 5 to me, if I'm understanding correctly. So I'm curious if you could say a little bit more about like why that happens and if you expect that's like sort of a universal prediction of this mechanism or not.
Yeah, so like this is such a simple simulation. I didn't want to be like, aha, see, like, but yeah, as you get closer, or basically get to lower semi-major axis orbits, your orbital period is shorter, secular timescales are shorter, so you're going to see the effects of eccentricity change much quicker as you go to lower semi-major axis orbits. Further out, it's just going to take a longer time. I've only run this for 10 million years. So I can't say confidently that you would still retain this bunch of objects down here. But I also want to change the surface density profile. Right now they match each other, which shouldn't be the case.
Was it uniform?
Its surface density profile is going as r to the -2. Upon reading more frantically this week, I believe it should be something like just like modeling the disk. I think standard one is going as r to the -1. So I'm going to change that in these simulations, but also scattering should actually have a steeper profile. And so you'll have fewer bodies out here, more bodies down here. And so it'll be easier to retain bodies in the outskirts of the Kuiper Belt. So maybe we can reproduce the Kuiper Canyon that way. But with these very simple simulations, I wouldn't want to claim. But thank you for noticing that. It's like it's suggestive, but I'm not sure.
Hi, thanks for the great talk. So, not sure how valid this question will be in this context, but in the case of galaxies, we see galactesimals, also known as stars, migrating to larger and larger radii, and you can have resonant interactions with spiral arms and bars that can kick stars to larger radii while increasing their orbital eccentricity. So I'm wondering, can a mechanism like this also operate in this context here? Because you want to increase the semi-major axis of the planetesimal along with increasing the orbital eccentricity. So can you have resonant interactions with, say, Neptune or even the inner planets inner to Neptune that can create something like this?
Not sure I followed the entire question. I have to say, I didn't get enough sleep last night, so this could be me. I was focused on galaxies, and now we're back at Neptune. I'm like, I've lost it. I've completely lost it. Could you say it again?
So just to summarize, could you have resonant interactions with Neptune and the planets that are inner to Neptune, like Jupiter and where is Uranus?
Yeah.
Yes, Uranus. And that can cause such a behavior where you are increasing the semi-major axis of the planetesimal along with increasing the orbital eccentricity.
So like Renu Malhotra's like mean motion resonance capture theory. So we could definitely do that. We just like in these simulations, we just need to actually physically put in the planets, which I fully intend to do. So that could be really interesting, like to actually have a migrating planet and see bodies captured into these resonances, and then see how the scattering bodies actually interact with those resonances. Just computationally ugly to do this, expensive, which is why people haven't done it. Typically just make these particles massless test particles. But yeah, it would be fun to see.
Ben?
So I have a question about the plot on your summary slide, the line of what is it, constant parity on the last slide.
Sorry, this is a lot of
Yeah,
animations.
no, it's okay.
Yes. I do know what
Also,
you're
I
talking
just
about.
wanted to point something out. I wasn't sure if this was intentional, but it seemed like the line of constant perihelion extended above eccentricity of 1, and I was wondering if that was just a limitation of the schematic, or if you were trying to represent retrograde
Yeah,
orbits there.
this is me just not paying attention and.
Yeah,
No, I do not mean to.
okay,
Like,
so,
they become unbound, but scatter back now.
but I have a more substantive question, which is if you make any predictions about populations of retrograde or out of plane orbits for the scattered objects. Because that would be something that could be compared to observations that should be very dependent on the scattering mechanism.
Yeah, I'm really interested in that because I'm just interested in Triton as well. It's a retrograde moon of Neptune. I'm so interested in, can you actually pump up the eccentricities to such an extent that you flip the orientation? So I am really interested in that, and I suggestively showed a plot for inclinations or flipping back and forth between 0 and 180. With a migrating Neptune, this could be really tricky. Just because, you're not allowed to go to an eccentricity of 1 and flip your orbit. You're going to go to a very high eccentricity, have a strong encounter with the planets that are migrating outwards, before you actually get to fully flip. So I will look more into it, but I don't have a solid kind of, yes, definitely going to produce retrograde bodies this way. I would love if we did.
Yeah, I think the extraplanarity also might be constraint of the outer solar system objects, the detached bodies and so on and so forth might have some use for probing whatever the scattering mechanism is that gets them out there.
I think it might be hard to get data for that because most people who are trying to detect solar system objects mainly stick to the plane of the solar system.
But we will have Vera Rubin.
Yes, I think Vera Rubin will be better at just recovering known objects and not so, well, I guess for the Kuiper Belt, it'll be good for this. For the inner solar system, not so good. For discovering things, just for securing the orbits of known objects. But for the Kuiper Belt, yeah, they're moving slow enough. I think it should be good.
Yeah. So.
Right, 4:34. Let's just think.